let's just take a moment to have a think about security on the web. And I want to think about it in two different ways. So number one, let's take a look at the server. Now this is both the web server and the database server, so everything that happens on the back end. Now all of this stuff is in your control as the person building the web application. You build the app, you possibly manage the infrastructure. This is centralized. This is the thing that the browsers connect to. So what are the sorts of security risks that we normally think about at this layer? Well, a good example is SQL injection. We need to make sure that our applications are resilient to an attacker trying to execute arbitrary SQL commands in the application. So validating untrusted data, parameterizing queries, all the sorts of things I talk about in courses like Ethical Hacking SQL Injection. Insufficient authorization is another great example. We're talking about access controls here. Does the web application make sure that the right people get access to the right things? This is very much a server-side control, so it's something that we have to get right centrally. Same again with weak credential storage. How you store passwords on the server is absolutely critical. Clearly, you don't want them to be in plain text. You also don't want them to be encrypted. And if that sounds odd, go and have a look at a course like the OWASP Top 10 for ASP.NET developers, and you'll see me talking a lot about password hashing. Now all of this is a server-side control. It happens in the web application. It's stored in the database. Now obviously, in any sort of web application ecosystem, complementing the server we have the browser. And there are a bunch of different threats that we have to deal with that manifest themselves via the browser. So cross-site scripting is a really good example. This is definitely something that we can defend against on the server side, but the execution of it is in the client. The browser actually has to run the attacker's script. So this is a threat that we can also address on the client. And that's one of the things that you're going to see when we get on to looking at content security policies later on in the course. Insufficient transport layer security is another good example. And again, we can control this to a degree on the server. We can make sure that requests are coming in via HTTPS, and there are various things we can do server-side to ensure connections are secure, but it's still the browser that's making insecure requests. So wouldn't it be great if we could be a lot more explicit in telling the browser what requests it must make securely? Not just now, but what about what requests it must make securely in the future? What certificates should it expect from the server? These are controls that we can implement in the browser by sending it the right security headers. Another good example is clickjacking. I talk about clickjacking in my Hack Yourself First How to Go on the Cyber Offense course. In fact, I show exactly how it works, and it is another attack that has to execute in the browser. Using security headers, we can tell the browser not to allow this style of attack to happen. So again, there's a lot that we can actually control in the browser. We just have to get the server to tell it the right things. And we're going to do that using these security headers. Now, when it comes to security on the web, there are a bunch of things the server simply can't control. Let's move on, and I'll show you what I mean by that. There's only so far we can go as server-side controls. Let me give you 3 good examples, and they align to the 3 different security headers that we're going to be talking about in this course. So first example is there's nothing to stop a client from making an insecure request to a website. So for example, someone could type in an insecure scheme. They could type in HTTP rather than HTTPS. Now under normal circumstances, the browser will issue that request and it will go out over an insecure channel. We're going to fix that with the HSTS header, or HTTP Strict Transport Security. Another good example is a certificate authority getting compromised. This happens. I'll give you some examples of this a bit later on. And the problem here is that if a CA does get compromised and a rogue certificate is issued, again, under normal circumstances, so long as that is actually a valid CA that the browser trusts, even though the certificate may have been illegally issued, the browser will trust it. We're going to fix that with the HPKP header, or HTTP public key pinning. Another good example of something that the server can't control is another website simply putting yours in a frame and then launching a clickjack attack on it. I just mentioned clickjacking, and it exploits the fact that most websites can be put inside a frame in another website, and an attacker can then trick the user into thinking that they're clicking on something else, but they're actually clicking on the target website. We're going to fix that with the CSP header, or Content Security Policy header. So all of these things here are risks that we simply can't address in the server alone. We can mitigate it on the server, but we can't fully solve these challenges server-side. And that's why we need these browser security headers. And they're a great complement for all the good controls that we should have running on the server. This is going to be very much about defense in depth, layer upon layer of security, such that we have no one single point of failure. And in fact, we have multiple layers of redundancy, which strengthens the security and gives us some great defensive capabilities against all sorts of different styles of attack. So that's what this course is about. Now, before we start looking at the actual security headers themselves, I want to just do a quick recap on exactly why we have headers. So let's move on and take a quick look at both request and response headers before we go much further. Let's take a really basic scenario. We've got a user here, the user has a browser, and the browser is going to make an HTTP request to a web application running on a server. It might look like this. This is an HTTP GET request to load the Pluralsight website. Now this is what your browser actually sends in the request. This is the header, and I'm just representing a few key attributes of the header here. So for example, we can see it's a GET request. It's not a POST or a PUT or a DELETE or any other HTTP verb, and clearly it's loading the home page of the pluralsight.com website. It's making the request over HTTP using version 1.1 of the protocol. We can see my user agent here, and although it looks a little bit odd, Windows NT 6.3 is actually Windows 8.1. The rest of the user agent string here gives us a little bit more info, the key thing here being that I'm using Chrome version 44. And obviously we get the minor version details as well. Now all of this is also sent along with my accept language header. And here we have the browser telling the server that my preferred language is English US. I will also accept English, but Chrome only has about an 80% level of confidence that I actually want English, the generic English, as opposed to English US. Now the point of all this is that this is a way of the browser sending instructions to the server. This is only the header. It's not the request body, such as a POST request, where we're actually sending user data to the server as well. These are all just instructions that are sent automatically by the browser on every single request. Now of course, after the server receives this request, it sends back a response, and the response itself has its own header, and it has its own set of attributes in that header. So it's confirming here we are talking HTTP 1.1. The response code is a 200, okay, so the request worked fine. Here's a valid response. We've got a cache control directive in here, so the browser knows what it should do with this resource in terms of caching it locally and not going out and requesting it again. The content type is declared. This is just a text/HTML page encoded in UTF-8, and we're also getting the date that the server decides to send back to the client. Now neither this request or response header is exhaustive. There's a bunch of other attributes as well. But I just wanted to point out that in each case, these headers are separate to the body, and the headers can give instruction, either to the server or the client, to tell it how it should behave. The cache control example is perfect. Here's how you, the browser, should behave in terms of keeping this data cached locally. Just to make this really clear, let's go and take a quick look at this in the browser. Here we are in the browser. I've got the developer tools open and I'm on the network tab. Let's load up that Pluralsight website, and then we'll drill down and have a look at both the request and the response headers. And what I want to do is just look at the ones on the very first request. So we'll scroll all the way up to the top. We'll choose that first request. And here we can see, first of all, the response headers. Chrome decides to put those first. So this is everything that the server is sending us back based on what the Pluralsight website believes our browser needs to know. When we scroll down a little bit, we'll also see the request headers. So everything the browser decided that Pluralsight needed to know when the request was sent to them. Now all of this is just about the client and the server communicating independently of the actual body of both the request and the response. It's a way of sending these instructions backwards and forwards. And that's precisely what we're going to do with browser security headers. We are going to add headers to the response that comes from the server back to the browser. So they're going to sit right in here in the response headers, alongside things like the content encoding and the content type. We're going to be adding HSTS, HPKP, and CSP headers right in here into the response. And not only are those headers going to tell the browser how it should handle security right now, it's going to tell it how it should handle it in the future as well. And in fact, in some cases, how it should handle it even many, many months into the future for the particular website that's sending those headers back in the response. Now there's one more thing I want to look at in terms of response headers before we go on and start talking about some of the security ones. And that's how the browser handles this once it actually receives those response headers. Here's a great example. We've seen this cache control directive in the response headers a couple of times now. Now what? What does the browser do? It's just received this header. What happens next? Well, the first thing is that the browser has to implement the header. So the browser has to look at something like cache control and say, I know what that is. I know what it is that I now need to do based on the instruction that the server has given me. And this is a really, really important thing. It is a client-side control. It's entirely up to the browser what it now does with this header. So as we start looking at security headers, it's really important to remember that they are just an instruction back to the browser. Now the browser may not even recognize it. And in fact, for a number of the headers we're going to look at, different versions of different browsers simply won't recognize them. Some of them are quite new. And that's fine if a browser doesn't know what to do with it. It will just ignore it. It will say, hey, I don't know what this header is, therefore nothing is going to happen. There is no adverse impact if a browser receives a header it doesn't recognize. It'll just ignore it. Now, it's not just headers that browsers will ignore if they don't recognize it. It applies to markup as well. And both do evolve over time, and inevitably we have cases where browsers receive headers or markup that they don't recognize, they don't know what to do with. They haven't had that paradigm built into it. Let me show you a resource we're going to use quite a bit throughout this course, and I'll give you an example of what I mean in terms of browser support. This is a fantastic resource, caniuse.com. And it's particularly valuable in an era where we still have a lot of different browsers and we have web standards moving forward quite quickly. And often you're left wondering, if I use a particular feature, will my audience actually be able to understand it? So I'll give you an example. We can search for, say, Canvas. And in fact, if we scroll down a little bit on this page, we can get a sense of the browser support for Canvas. And Canvas is pretty well supported in the current day. It's really only IE8 in terms of browsers of recent years that doesn't support it. So you could look at this and say, I can use Canvas, and pretty much everyone that loads my site will do so with the browser that understands what the Canvas tag actually does. Now we can see some global stats here that tell us that 91.13% of browsers fully support Canvas, 4.74% partially support it. And if we're really worried about IE8, we can hover over it and we can see that the global usage of IE8 is apparently only about 1.5%. So we probably wouldn't be too worried about using the Canvas tag and such a small percentage of browsers not understanding what it does. Now down on Opera Mini, we can see version 8 represented in a different color and a number 2 in the corner. And if we scroll down a little bit further again, we can see that whilst Opera Mini does actually support the canvas element, it's not able to play animations or run more complex applications. So we want to be a little bit conscious of that if that small audience, which is 4.62% globally, was actually important to us. Now, as we start looking at these security headers, at the end of each module, we're going to look at caniuse.com to see how well supported the header is. And we'll see a similar set of stats for each one of those 3 headers. So we're going to use this resource a lot. It is really valuable. And I strongly encourage you to refer to caniuse.com if you're curious about how well supported these headers actually are. But again, if the browser doesn't recognize the header, it'll just ignore it. There is no adverse result. The worst that happens is users with a browser that doesn't recognize it doesn't get the security defense that people with a supported browser get. But given all this is an additional layer on top of the other good security practices, that's not too much of a problem. With that now understood, let's move on and take a quick look at some non-standard and browser prefixed headers, which we consciously won't be covering in this course. The thing about browser headers, and indeed many aspects of HTML and other web technologies like CSS, is that they do go through multiple iterations before being formalized and ratified by the W3C. Now, as a result of that, we often have these legacy artifacts, and that might be anything from HTML tags through to browser headers, such as the ones we're going to look at here. Now, often these are experimental, and there's no real guarantee of them being supported into the longer term, even though some of them may have actually been quite broadly used. The idea of this course is we're going to focus on the candidate recommendations of browser security headers. So these are the headers that are going to be around for the long term. And that's really important because there's no point focusing on the ones that were just experimental and have now been superseded. So let me give you some examples. The X Content Security Policy header. This was experimental, and it was introduced back in the Gecko 2 based browser days. So earlier versions of Firefox, Thunderbird, SeaMonkey. This has now been replaced by the Content Security Policy, so no more X. Keeping in mind that the X prefix indicates a non-standard header. So when we look at one like X WebKit CSP, we're looking at a non-standard header that is also browser prefixed. Okay, WebKit is actually a layout engine, but the point remains that it's a specific implementation designed to render web applications. And again, it is an X prefix, it was non-standard, and it has been replaced by the Content Security Policy header. X-Frame Options, often known as XFO, is another non-standard one that's been replaced by CSP with the Frame Ancestors Directive. We're going to look at that in more detail in the CSP module. But again, it's gone, we don't need that anymore, certainly not for modern browsers that actually recognize CSPs. And finally, XSS Protection. Now this header was primarily used for actually blocking the browser's XSS filter, which is really not something you want to be doing. Modern browsers have a level of XSS defense built into them to try and protect users from reflected cross-site scripting. You don't want to go disabling that, and it is also a non-standard header. So this is not a header that we need to cover in this course. We're going to focus on all the stuff that is actually going to be around for the long term and is being implemented into browsers right now. To give you a sense of how broadly used these security headers actually are, the last thing I want to do before we wrap up this introduction module is go and take a look at the current utilization of browser security headers in the top 1 million sites on the web today. I want to give you a sense of how much browser security headers are being used because it does actually tell quite a significant story. And indeed, it's one of the reasons why I'm creating this course. Now, these are all relevant at the time of recording in August 2015. And all of these figures come from a security researcher named Scott Helm. You can find him at scotthelm.co.uk. Scott's given me a heap of great info that's gone into this course, and you'll see his name repeated across the coming modules. But one of the things he's done in order to demonstrate the lack of usage of browser security headers is scan the top 1 million sites on the internet as defined by the Alexa rankings. Now the next couple of modules we're going to cover on HSTS and HPKP all relate to HTTPS. So one of the first things Scott did is took a look at how many sites are actually enforcing HTTPS. And it's not very many. 7% are redirecting any HTTP requests to HTTPS. Only 7%. So 93% of sites in that top million are quite happy to be requested insecurely. Now of that 7%, only a very small portion are using the HSTS header. So roughly 1/7 of the 7% of sites using HTTPS are sending back this header. So it's about 1% of the top 1 million sites on the internet. So that's a pretty small figure, and it goes to show just how underutilized this browser header is. But if this figure looks small, let's go on and have a look at the other ones. So that was HSTS. The other one is HPKP, and only 169 in total, 169 sites out of the top 1 million are using HPKP. So that actually rounds down to 0%. It's as good as no websites at all are using this particular security header. It's extremely rare, which is very unfortunate because it's also extremely powerful, and you'll see exactly how powerful in just a moment. Now both HSTS and HPKP are only going to appear on HTTPS sites. The other browser header I want to show you while we're looking at statistics is CSP. Let's have a look at that. That is an alarmingly small number. About 1,500 websites out of the top 1 million are using a CSP. Now CSPs aren't dependent on HTTPS. You can put a CSP on any website regardless of which scheme it's normally loaded over. And CSPs are also enormously configurable. It's very easy to drop them into a website and be enormously liberal in their configuration. So there's really no reason not to use them. And they are actually supported by the majority of people browsing the web as well. Certainly the browsers used by the majority of people browsing the web. But they're down at 1,500. Very, very low utilization. And again, I hope that this course helps people see the value of browser security headers and starts to pump these figures up a bit because they deserve to be more broadly used. They're enormously valuable. So that's the introduction. Let's go and summarize the module before we move on to actually starting to look at security headers in detail. Let's summarize the module. And the first thing I hope I made really clear is that these browser security headers are a client control. This is going to help us secure things better in the browser. It's not a server-side control. We're going to send the security header from the server, but it's up to the client to implement it. It is an additional layer of defense. We still need to protect our server-side applications using all the well-established security practices to defend against risks at that layer. But this is a great additional layer. Again, defense in depth. Now these headers are also evolving. Some of these headers are no longer used. I showed you a bunch of Prefixed or even browser/layout engine prefixed headers earlier on, which have now been superseded by successors that should be around for the long term. Now, of course, some of these are not actually even recognized. But as I said, it doesn't matter if the browser receives a header that it doesn't know what to do with. It'll just ignore it. There really isn't a downside to the browser receiving it and not knowing what to do. And finally, as we just saw, these browser security headers are massively underutilized. HPKP and CSP in particular, rounding down to 0% utilization in that top 1 million websites. We need to get these figures up. These are great security controls. They're easy to implement and they come for free. And one of the best things we could do for security on the web is to start to get them more broadly utilized. So with that said, let's jump into the course and start looking at exactly what they do and how you can get them working in your web applications.